In today's video, we shall look at alternating currents. Before we discuss alternating currents, let's revisit direct current. Let's look at a very simple direct current circuit, like this one. So you have a battery, and it's connected to a resistor, say with resistance R. So this is a positive terminal of the battery, and that is the negative terminal of the battery. Let's assume the voltage is V. In such a circuit, the current goes exactly in one direction, as shown by the arrow, and the voltage can be related to this electric current in a following manner. Nothing changes, the value of V is the same, and the value of the electric current I is also the same, because R is a constant. Now I'm going to substitute the battery with an alternating current source, such as the one shown here. So the usual circuit diagram symbol for an AC source is like that. So this AC source creates a sinusoidal voltage, and it's given by the following expression: V cosine omega t. Little v is the instantaneous voltage, capital V is the voltage amplitude, and omega is the angular frequency. The question is, angular frequency of what? For an AC source, it creates an electric current, for example, initially like that. And after some time, the direction of that current I reverses, like this. So the flip in the direction of the current from like that to like that is controlled by this number. This flip represents one cycle. If, say, the frequency of that AC source is 50 Hz, or since omega is 2 pi f, omega is 100 radian per second, that means this AC source with a frequency of 50 Hz creates 50 such cycles every second. Or each cycle takes a time of 0.02 seconds. So that is the significance of frequency or angular frequency of an AC source. If the instantaneous voltage in the circuit is given by this expression, the instantaneous current is given by a similar expression, the current amplitude times cosine omega t. Because after all, V is I, R, and if little v is capital V cosine omega t, I capital R, you see I is just amplitude of that voltage over resistance times cosine omega t. And this is just the current amplitude. We note that since the value of V, and therefore I, can be positive or negative due to fluctuations like that, it is more useful to describe the average value of such quantities using the concept of a root mean square. So if you want to calculate the root mean square value of voltage, first you have to calculate the average value of the square of the voltage, like that. The right-hand side of this expression consists of a constant, the amplitude of the voltage, and a function that is function of time. So the average value of the square of the amplitude is quite simply v squared. The average value of the square of cosine can be determined from calculus, and it can be shown that this is indeed half, and you get that. So the root mean square value of a sinusoidal voltage is given by the following expression: square root average value of the square, and that is quite simply the voltage amplitude over square root of 2. So this is what we call as root mean square value of the voltage, the oscillating voltage. Likewise, the root mean square of the oscillating current is given as the current amplitude over square root 2. We note that For such a circuit in which there's only resistor in that AC circuit, both current and voltage are represented by the same oscillating function, namely, for current is capital I cosine omega t, for voltage capital V cosine omega t. So they are both proportional to cosine omega t. So we say that I, namely the electric current, and voltage are in phase with each other. The best way to see this is by plotting the so-called phasor diagram, which will show the current and voltage as functions of time. And they are shown as rotating vectors. If I take the electric current to be of that arrow, the length of which refers to the amplitude of the current, the projection on the time axis, like that, is the instantaneous current I. And this angle here is omega t. Since electric current and voltage are in phase with each other, I can also represent the voltage as another arrow coincide with the current arrow, like that, the length of which is the voltage amplitude, and the projection is the instantaneous voltage, which is also rotating, and they rotate in phase because both have the cosine omega t in the expressions. So in AC circuits, phasor diagram can prove to be an important and useful tool in analyzing circuit. Now what if you have inductor in the circuit? Let's assume at some point in time the current is going that way, and the current is given by the following expression: current amplitude times cosine omega t. We have seen before from our previous video on inductor that the potential difference of voltage between such 2 points is given by L, inductance that is, times di dt. Since I is given by that, di dt is given by minus I omega sine omega t, which can be rewritten in terms of cosine as follows: I omega L cosine omega t plus 90 degrees. Now let's look at these two expressions. What it shows is that V leads the current by 90 degrees in a circuit containing inductor. So if the current phasor is going like that, the voltage phasor will be like that, with the angle between them being 90 degrees, and the rotation is that way. So V leads I by 90 degrees. This expression is the amplitude of the voltage. It's given by I omega L, and that is what we call the reactance of the inductor, or inductive reactance. It is quantified in the same unit as ohm. Although it has the same unit as resistance, it is fundamentally different from resistance in the sense that it is dependent on the frequency of that AC source and also the value of the inductance of the inductor. Now what happens if you have a capacitor in that AC circuit? Like that. So this is a capacitor with capacitance C. At any time t, let's assume the current is I in the circuit, and let's assume the oscillating current is given by that expression, cosine omega t expression. What can you say about the voltage between points A and B? Since voltage is related to the charge, from that expression we need to figure out the charge on that capacitor at any time t. Electric current is rate of change of charge. So in order to get charge as a function of time, you need to integrate that expression. And you're going to get I over omega. Integrating cosine, you get sine omega t. Putting that in here, you get the potential difference between points A and B to be Q over C, or quite simply, I over omega C sine omega t. And you can write it in terms of cosine as follows: I over omega C cosine omega t minus 90 degrees. Obviously, the current and voltage are not in phase. The phases are different. Indeed, we see from the expression that voltage indeed lags I by 90 degrees. So in the phasor diagram, if I is represented by that, the projection is of course the instantaneous current little I. The voltage is represented by that rotating phasor. The angle between them is 90 degrees and you see V lags the electric current. This expression, which refers to the amplitude of the voltage, can be slightly rewritten like that, where x sub c is 1 over omega times the capacitance. This is known as capacitive reactance, with the same unit as unit for resistance, namely ohm. And you see that this capacitive reactance as opposed to resistance is dependent on the frequency and also the capacitance of the capacitor. Let's look at the following problem. A 300 ohm resistor is connected in series with 6 microfarad capacitor. The voltage across the resistor is given by that expression. What is the circuit current? The circuit current, as we have seen before, must be in phase with the potential difference across the resistor. So we can write it as the amplitude of the electric current times cosine 2500 t, where the amplitude of the current is given by the amplitude of the voltage 1.5 divided by the resistance of that resistor, namely 300 ohms, cosine 2500 t. And the answer is I as a function of time is 5 times 10 to the power minus 3 cosine 2500 t, of course measured in the units of ampere. Part B, find the capacitive reactance of the capacitor. So capacitive reactance is given by 1 over angular frequency times the capacitance. Now the angular frequency can be determined from that expression, or that expression is 2500, so 1 over 2500. The capacitance is 6 microfarad, so 6 times 10 to the power minus 6 farad. The answer is in the unit of ohms, which will give you about 66.7 ohms. And finally, what is the voltage across the capacitor? That is as a function of time. And that is given by the current amplitude times the capacitive reactance. So that is the amplitude of the voltage. Now this is a capacitor that is in the AC circuit. So the voltage across the capacitor must lag the current by 90 degrees. So that means it's cosine 2500 t minus 90 degrees. Well, since this is in radian per second, we can write the 90 degrees in radians, and that's going to be pi over 2. The current amplitude is that number. Capacitive reactance is that, so that times that will give you 0.334 for the voltage amplitude, and that times cosine 2500 t minus 90 degrees gives the instantaneous voltage across the capacitor in this circuit. And that solves the problem. Thank you for watching.